machine learning techniques. Duo received his bachelor in astronomy at Nanjing University, then moved on to the National Astronomical Observatories at the Chinese Academy of Sciences, obtaining his MA in astrophysics with D. Li. Then he moved on to UMass Amherst, where he began working with Stella, and they both moved on to UT Austin in 2017. From my own experience, I know how challenging it is to accurately identify the sites of stellar feedback, and I'm very much looking forward to hearing about the new techniques being developed by Duo. So without further ado, please take it away.
Thanks for a nice introduction. Okay, hello everyone. Today I will introduce our work on application of machine learning to identify stellar feedback structures. And we have published 2 papers here. If you're interested, please go to that archive paper for detail. First, in both simulations and observations, feedback exists across all physical scales, from sub-parsec scale molecular outflow to a parsec scale stellar wind-driven bubbles or radiation-driven bubbles, or tens of parsec scale supernova bubbles, even kiloparsec scale of AGN jets or AGN feedback. All these feedback mechanisms are important to regulate the evolution of the universe. In terms of our local solar neighborhood, stellar feedback is crucial. It regulates star formation process and possibly compensate the dissipation of turbulence. There are 2 typical types of feedback, stellar feedback. One is collimated outflow. The other is more isotropic stellar wind-driven bubbles. Both mechanisms will shape the morphology of the mega cloud. And this feedback will also create shocks and trigger some complicated chemical reactions. In simulation, we see stellar feedback reduce both star formation rate and star formation efficiency. And it's really clear stellar feedback plays an important role, regulates star formation. In terms of energy budget, for example, in Perseus, stellar feedback contributes significant amount of kinetic energy to the host cloud. The total kinetic energy coming from bubbles or stellar winds is comparable or half of the turbulent energy. If we compare the injection energy rate from the bubbles to the dissipation rate of turbulence in Perseus, we see these 2 ratio or 2 rates are almost equal. So that means turbulence can be compensated by stellar feedback, or stellar feedback is sufficient to maintain turbulence at the current epoch. And the similar results is also found in Taurus cloud. Besides energy, stellar feedback also affects turbulence globally. In simulation, we see stellar winds flatten the spatial power spectra of the velocity field. Here, we see the slope is flattened, which indicates there are energy or mass injected into larger scale. And also here, we compare the gas where there is no direct contaction with feedback. So that indicates energy can be injected via larger scale without direct connection. They can be transferred by magnetic wave, for example. Then feedback can also be highlighted in some statistical quantity, for example, covariance matrix. Here are the synthetic observation. We conduct synthetic observation with feedback and without feedback. We see there are off-diagonal signature, which indicates the high velocity component or coherent have a loss in motion blobs that are coming from stellar feedback. So this quantity can give us some hint where there is feedback. I just gave a really brief review on the importance of stellar feedback. So in the following talk, I will introduce two machine learning approaches to identify stellar feedback structures. Then I will talk about some statistical studies on stellar feedback. To study stellar feedback, the main question is how to identify stellar feedback structures. If we look at Spitzer image of a galactic plane, we see feedback is everywhere. There are multiple bubbles and they are overlapping with each other. It's really hard for human to disentangle these bubbles by eye. So that's why we cannot, or we are almost impossible to get a complete census of the number or the mass of feedback by visual inspection. There is one way we could do, that is ask citizen scientists to help us to circle where the bubble is. So this is the nuclear project. But there is some disadvantage for this project because different people will have different opinion of the position or the thickness of the bubble. And also that is not repeatable. So that's really hard for us to calibrate of where or the position of the feedback is. So that's why we need machine learning to help us, which is reproducible and also easy to calibrate based on simulation. Moreover, as I showed the plot before, in simulation, we definitely see stellar feedback can reduce star formation efficiency and star formation rate. However, in observation, we didn't see the trend. If we compare the energy coming from feedback and the star formation efficiency and the calculated star formation efficiency, we didn't see a trend or relation between these two. There are several reasons might cause this, such as whether our estimation of energy coming from feedback is correct. There might be some interloops, or there are some missing samples. And also, how we calculate the top efficiency is also under debate. So that's why machine learning might provide us some approach to better quantify the mass, energy, and the momentum coming from stellar feedback. And machine learning, they have several advantages because they are really fast, especially on GPUs. And also they are repeatable. We can do several tests across different platforms, and they are almost perform consistently. Moreover, machine learning can give us some hidden prediction where human is not able to derive from the data. So that's predicting some hidden information or predicting some unknowns. First, I will introduce our machine learning approach to identify feedback bubbles in dust emission. The algorithm we use here is called random forest, which is a decision tree. The algorithm will make a series of decisions on an object. For example, if we want to classify different animals, such as for cats, birds, or bears, if we make several criteria to determine whether these objects follow this criteria. It has 4 legs. Okay, that's not a bird. Its mass is below 10 kilograms. It's not a bear. At the end, we will classify different objects into different categories. For bubbles, we extract the features which best describe the morphology of bubbles and then conduct this classification. The data we use here is dust emission from Spitzer, including 4.5 micron, 8 micron, and 24 micron including hot dust emission and pH emission. We started with McGill hydrodynamic simulation, which model the stellar winds, driving stellar winds in a piece of a McGill cloud. Then we conduct dust radial transfer to generate dust emission of bubbles in Spitzer band. And this is part of our training set. Then we combine observation. There are bubbles identified by citizen scientists in Milky Way project, where there are observational bubbles. By combining these two, part of simulation bubbles and part of observational bubbles, and train the algorithm. And we could give a classification of an object, whether it's a bubble or not. It will return the score, or the score indicating the probability. The higher means the higher chance of this object is a bubble. To enhance the diversity of our training set, we adopt simulations with different stellar winds, with different evolution stage, with different turbulence, and with different magnetic fields. And to simulate the dust emission, we also adopt different dust model when we do radial transfer. And we adopt different dust model and to replicate almost same feature as observation, such as here, we could recreate some pH emission compared to the real data. And if we compare the synthetic data and real data, they are almost similar. And after we retrain our algorithm by containing or by supplement some synthetic data, we see the performance of this model is enhanced. If we only train the model with observational bubbles, there are some bias. We cannot identify the yellow bubbles, which are driven by relatively lower mass star, such as B-type star. Because for human, we have bias towards really bright things. In real data, people are always identifying bright red bubbles, which are driven by O-type star. Our simulation will compensate for this bias, and we implement by adding some synthetic data, such as yellow bubbles, and enhance, we see there is a huge improvement in identification of the bubbles, and also we identify more yellow bubbles than before. So this project gives us confidence that synthetic data really helps in classification. However, feedback is not limited in two-dimensional. The feedback is kinematic in 3D. So if we want to study the dynamic structure of feedback, we need to go from dust emission to molecular line transition, where we have velocity information. However, for random forest, it's really difficult to extract this feature in three-dimensional data. And also, it's really computationally expensive for random forest. That's why we switched to a new method. We use convolutional neural network to extract where the bubble is in 3D data. For convolutional neural network, it's really fast and no need for manually feature extraction. And also it's insensitive, it's not sensitive to the position of bubbles. I will introduce our new method using convolutional neural network to identify bubbles and outflows in molecular line emission. I will give a really brief introduction of what is convolutional neural network. The basic idea of this method is by applying different filters to extract different features of an image. And by break this feature map into different pieces, then at the end, we will conduct classification. We follow the same strategy and develop a convolutional approach to structure identification, CASI 3D, in our project. The basic idea is we have two parts, the encoder part and decoder part. The encoder part will extract the features from the raw input data. Here, the input data is a data cube. The position, velocity is a spectral data cube. And the encoder part will break this into pieces. Then the decoder part will translate these features into another data cube with the same shape, position, velocity indicates where the feedback is. So they have the same shape, and the input is the raw emission. The output is the position or the location where the feedback is. And our project is public on GitLab, and we have the algorithm and also the training model. Feel free to download and try that on your real data. We started with like the hydrodynamic simulation, which launches the protostar launching outflow in a piece of McGill cloud. Then we conduct synthetic observation to generate 12-cell emission from the host cloud. And in simulation, we can trace or track the position of feedback. So we know which voxel has feedback mass. So this is the tracer field. We also conduct synthetic observation of the mass where there is only feedback. So the input is the 12-cell emission. The output will give us the mask where the feedback is. Then we train the algorithm with this input data. After training, we are testing our data not only on synthetic data, we also test that on real data. This is the observational data. The blue is 12-cell emission of a Perseus cloud. And the red is the prediction, indicating where feedback is or where outflow is. Then we extend our method into larger map, indicates where the outflow is. The red boxes are the previously identified outflow, and the yellow boxes are the newly identified outflow, and label O and Y indicating the young star objects at older evolution stage or younger evolution stage. And different contour indicates the position of outflow, red lobe or blue lobe. Similarly, to enhance our training set, we adopt different turbulence, different magnetic fields, and different stage. And also when we do our synchronization, we adopt different cell abundances and different cloud temperatures to simulate different physical and chemical condition of the cloud. And for this work, we develop two tasks. The first is what a human will do. That is, give us a mask of the position where there is feedback. And the second task goes one step further. And this will give us the correction factor of each voxel where there is feedback, and give us the correction of the mass in each voxel. Because if we calculate the mass in PPV data cube, in each voxel, the emission is not all comes from feedback. There are contamination from foreground or background, or the gas that are located at a similar velocity range, but they are not associated with feedback. So this will give us a better estimation on mass, energy, and momentum. Here is the performance on the test data. The tracer is the ground truth, and ME1 is giving the position, MF gives the mass correction, and both are able to identify the morphology. And here, we test our data on a real outflow in Perseus molecular cloud. And the contour is our prediction. And this is different channel, or last channel, from -2 to 15. And to mention that in our method, we are not giving the prior of the position of YSO. Our algorithm is purely morphology-based detection. But this detection is more close or associated with where the star is. So this gives us confidence that our algorithm is doing some reasonable job because our detection is associated with where there are stars that's driving this high velocity cloud or high velocity blob or feedback. To better visualize the prediction or the performance of our model, here is the three-dimensional visualization of our prediction. The blue is 12-cell emission of a piece of molecular cloud in Perseus, and the red is the prediction where there is outflow. If we give a velocity position velocity cut across this outflow, we can see this model is able to highlight this high velocity feature, coherent high velocity blob that are associated with young stars. So we can exclude its rest frame contamination from the host cloud and give us a pixel level prediction on the position of feedback. Besides for the previously identified feedback or outflow, our methods are able to identify some new outflows. Here is an example where there is a newly identified outflow in Perseus, and there are several young stars around it, but we are not sure which star driving this outflow. If we give a velocity cut on this outflow, both model is able to identify this high velocity feature clearly. Since MF is the correction factor of the mass, at higher velocity channel, this fraction will be larger. The closer to the rest frame, the fraction will drop because there are more contamination from the rest frame velocity gas. So that prediction is less extended than MU1 model. Then, in simulation, we know exactly the mass or energy or momentum comes from feedback or comes from the young star. And we conduct a similar approach as what observers do and compare that with the true energy, momentum, and mass comes from feedback. The true mass is derived from simulation. And the y-axis is we calculate the mass based on 12-cell and 13-cell we correct for optical depth and assume a constant excitation temperature, 25 Kelvin, which is widely used in outflow calculation. ME1 just gave us the mask where there's feedback. By adding that up, we see there is a factor of 5 overestimating because there is contamination from the host cloud or foreground or background. If we correct this mass using our model MF, this value is located similarly at one-to-one line. So this is the true mass. But there is still huge scatter because the complicated chemical or physical conditions. Similarly, we could retrieve the one-dimensional momentum. Since we only know the line of sight momentum, if we want to derive from one-dimensional momentum to three-dimensional momentum, we need to assume an exchange angle of an outflow and conduct a correction. However, there is no constant correction factor for this outflow, for individual outflow, because different outflow will have different orientation. That's just really naturally distributed. If we add them up, we can see statistically, if we assume the outflow are randomly orientated, then an exchange angle between 30 to 60 can roughly retrieve the total true 3D momentum. But there is no constant correction factor between 1D to 3D, since there's a huge scatter in this plot for MF model. Similarly, for energy, there is no constant correction. So our next step is to predict the correction factor or the exchange angle of an outflow to better calculate the energy and momentum from the stars. Then we use our method to calculate the mass of outflow for real outflow in Perseus and compare to what observers do in the past. Observers are usually calculate the mass of outflow by adding up the outflow channel. So that is where the outflow is most distinct, and draw a box located around the outflow and add up all the mass in that box. And then that's the outflow mass. However, there is contamination at this outflow with low velocity channels because there are contamination from host cloud. Also, on the other hand, there are some gas coming from feedback, but they are located near the rest frame. Observers are usually ignore that because it's really hard to disentangle the morphology near the rest frame velocity. So there are some missing mass. So these two are compensate with each other. There's a cancellation error here. There are missing mass, but also there is contamination from the host cloud. By adding these two, statistically, the true outflow mass from our model prediction is comparable to what observers do in the past. Similarly, for one-dimensional energy and one-dimensional momentum, our model prediction is consistent with previously estimation. Here, we show a statistical analysis for Perseus outflow. This quantity is defined as the mass predicted by our model. So it's the true mass by excluding the contamination at outflow velocity channel over the out velocity channel. Since at outflow velocity channel, there are higher fraction and there are more clear morphology. All outflow velocity channels, so that indicates there are more gas located at or near the rest frame velocity. So the larger the ratio, indicating there are more mass distributed at higher velocity channel. And this is what we see, or is consistent with our intuition. For older evolution stage YSOs, their ratio is larger than the young stellar objects driven outflows, because more gas is more likely to be ejected to higher velocity at later evolution stage. And more gas are likely to be observable in CO at higher velocity for older YSOs. So this is consistent with our outflow model. Then we have defined or identified outflows. Similarly, we could also identify bubbles in cell emission. The method is identical. They are almost same. The only difference is the training set. Instead of outflow simulation, here we use instead of wind simulation. And here we switch from 12 cell to 13 cell in structure identification because for 12 cell is too optically thick to discover or to identify the morphology of bubbles. But for 13 cell, it's more optically thin and the morphology is clear. And also, we adopt different physical parameter and different physical conditions in our simulation, and also different physical and chemical conditions in our synthetic observation. Here is how our model performs on a test data. This is synthetic data. CO tracer is the ground truth, which indicates the ground truth of the position of outflow of bubble, and both model is able to identify this bubble morphology or rim clear. Then I will show how our model performs on real data. This is a bubble identified in Taurus cloud, and blue is 13 cell emission, and our model is predicted in red. And our model is able to predict this rim clearly and also consistent with the coherent high velocity blobs or features that are associated with bubble rim. Then we can also quantify the mass, energy, and momentum comes from feedback for bubbles using our two models. Our model MF is able to correctly retrieve the true mass and true momentum. Then we compare our estimation to what observers do in the past. The blue is ME1 model. So this is consistent with what humans do. Because human or observer usually give a template of the position of bubbles and then calculate the mass based on this template. And our model is able to retrieve this one-to-one line. However, as I mentioned before, there is contamination. There are some gas comes from host cloud that are not associated with feedback. After correcting for this contamination, our model predict the mass decrease by a factor of 10. So there is order of magnitude difference here. So that indicates the actual mass or energy or momentum is decreased by a factor of 10 compared to previously estimation. So the conclusion about whether energy or momentum is able to compensate the dissipation of turbulence may not hold anymore. Here is the large map prediction of our method. Red boxes indicates some high confidence bubble, which with a star and also which are also identified before. The background is 13 cell emission, and this orange arc are the previously identified bubbles. Orange arc, and the red or pinkish overlaid is our model prediction, and the stars indicating the position of youngster objects, and yellow boxes indicating some of the newly identified bubbles, which are not identified before, where there is central star driving these bubbles, and also highlight stream where there's a cluster here. However, we also find some low content bubble. There are some bubble morphology. However, there's no known stars around it. So we don't know whether they are driven by some unknown stars, or the star has a higher motion move out of this field of view, or this might be caused by turbulence, where their morphology also similar to bubbles or ring-like structures. We have pixel level prediction of where the feedback is. Then we could do some statistical study on self-feedback. The most important part is energy budget. If we correct for the contamination, we see this mass comes from feedback will reduce by a lot, by order of magnitude. And we know in Taurus, the total mass, the total H2 mass is about 10,000 to 20,000 solar mass. And the star's mass, the young star's mass in Taurus is around 300. And this number is roughly 2%. And that number is also consistent with the star's mass. The previous estimation indicates almost 10% of the mass comes from feedback, or 10% of the mass are stars. So that's too high. And our new estimation is consistent to our intuition, because usually stellar wind's mass loss is comparable to the central star's mass. And our new mass is reasonable in terms of star formation efficiency and star formation rate in Taurus. And if we assume our new estimation is correct, we see the energy will decrease by a factor of 10. Then, if we compare the dissipation rate and the energy injection rate from our model, previously estimation is comparable, but now that's only 10%. That indicates bubbles in Taurus are not sufficient to support turbulence or the turbulent dissipation. There must be other mechanism to support the dissipation of turbulence in Taurus. Then we calculate the power spectra of feedback region and compare that to the entire region. Here is what is the spatial power spectra on an intensity map of 12CO in Perseus. This is the power spectra of the full map. And here is I exclude any noise region. So there is only emitting region. And the bottom two panel are the feedback region. So that is where there is feedback in the integration map. We see compared to the full map or the entire map prediction, the slope in feedback region is flattened. That indicates mass or energy might be injected at smaller scale by feedback. Similar results also found in 13CO emission in Taurus. Both slope in feedback region flattened. Then we revisit statistical quantity, covariance matrix. Our model is able to highlight this off-diagonal signature, which indicates the coherent high velocity motion, blobs or gas that might associated with feedback. So our model is doing some reasonable job. Then I just want to say our model can give us some pixel level prediction. Especially for human, we are really difficult to identify feedback, outflow, or bubbles in an extreme active star-forming region. For example, in NGC 1333, there are over 20 white cells in a parsec scale box. We could say feedback or outflow are everywhere. And our model, if we give a PV cut, position velocity cut, our model is able to highlight these high velocity blobs clearly and exclude the contamination near the rest frame velocity channels. But we don't know whether they are performing reasonable because we only trained our model on individual outflows and also or 2 or 3 outflows interacting with each other. We haven't adding an extreme star-forming region simulation in our model. And we are running the new model and to better quantify the performance of our model. So that means machine learning is able to learn from something and then extend to a wider aspect. That might give us confidence, the powerful of machine learning. And next step is definitely extend our model to more active star-forming region or more distant star-forming regions. With a better quantification of feedback, we might be able to reduce the gap between simulation and observation because we are able to have a better estimation of feedback, and then we could compare the actual feedback mass or energy and then compare to their self-emission rate or self-efficiency. Then our model are not limited to cell emission. It's able to extend to other molecular tracers. We just change the training set, then that's straightforward. For example, this is the low-effective ammonia emission observed by GPT. And we do a preliminary test on cell data in the similar region. In cell, this region is extremely noisy, and humans are really difficult to identify this feedback structure. Ammonia might be clearly since it's more optically thin, it might be easier to identify features. So we could extend our model to different tracers to better quantify stellar feedback. The most important part, or the most powerful part of machine learning is it's able to infer some hidden information, such as the fraction of mass associated with feedback, excluding the contamination. Then we are proposed to do some other tests to use machine learning to predict some intrinsic properties related to feedback or radio transfer properties, such as outflow launch velocities. Then there are some other more basic questions, such as how feedback drives turbulence. Since turbulence is difficult to quantify in observation because we don't know the full 3-dimensional density field or full 3-dimensional velocity field. In simulation, it's really straightforward to quantify how feedback or how turbulence is driven, solenoidal or compressive. But in observation, we only have part of the density and part of the velocity. It's projected PPV data. So machine learning might help us to give us some hints on how feedback drives turbulence. And we have some preliminary results in predicting the velocity, correcting for the velocity. For example, here is the ground truth, and there's the prediction. We predict the fraction of mean perpendicular to our line of sight. So the larger means there are more momentum or velocity are missing on the left side. So that will give us better quantification of the three-dimensional dynamic analysis related to feedback. So here I want to re-emphasize that our CASI 3D model is a really general tool. It's not limited to structure identification. It's also able to predict some hidden information, such as the mass or radial transfer properties or turbulence properties. And the algorithm is public, and feel free to download and use that. To sum up, the main takeaway is simulation provides us an efficient way to enhance the performance of machine learning. It will reduce the bias from human. And also, we're overestimating the mass comes from feedback by orders of magnitude. And so that means feedback is not sufficient to support turbulence or the dissipation of turbulence. Then both quantities, power spectra and convex matrix, indicating the presence of feedback, and feedback injecting energy or mass at smaller scale from our study in low mass star forming region. And I will stop here and take any questions. Thanks.
Okay, thanks, Joe. I think Carolina is off to another meeting, so I'll take it up from here. So thank you, and I'll clap for everyone else. So questions. So I have a question. So going back to when you talked about how in the Taurus region, the feedback, like there's not enough like energy coming from those sites of feedback to account for the turbulence in the, I'm gonna guess, the entire Taurus region. But you also mentioned how those features itself, because they turns out they are not correlated with the locations of the YSOs. They might be coming from turbulence themselves. So like, how do I reconcile the two?
That's a great question, because our model is only morphology based. So that's only identifying the feature where they have coherent, have velocity gas, and their morphology is similar to bubbles or outflows. If human cannot disentangle the morphology caused by turbulence or YSOs, then this algorithm cannot identify either, because it's purely morphology based. If we assume these patterns are not caused by turbulence, then another question is where the star is. If they are missing incoming sample or proper motion, we are not sure about that. And regarding to the mass estimation, sure, these are interloops if we assume they are caused by turbulence. But in our training set, we implement the pure turbulent box where there's no stars, but turbulence also have patterns where they have ring-like structure that may cause purely by turbulence, but their kinematic structure is not similar as feedback because they are not coherent across several velocity channels. So we still believe if we see a structure that has coherent high velocity gas feature, then that might caused by some dynamical process from stars or cloud collocation, but not purely by turbulence. So that also compensates for kinematic energy for the cloud. Yeah, that's great, but that's still debatable for that. But the interloops are not that much as we see here.
Okay. Other questions?
If I can ask,
Go ahead.
raise my hand. Sure. Nice talk, Joe. So I have a question. Have you also implemented this algorithm maybe on other star forming complexes apart from Perseus, like W49 and W50, where we have very good Herschel data available?
Yeah, sure. Straightforward. That's straightforward to do that. And we have tested our data on, and accuracy shows.
And second question.
Mhm.
Sorry, go on.
Yeah, for Herschel, I'm not sure if that is dust emission or spectral. Since for Herschel, there's still some spectral observation. You mean
You're
the
not-
dust emission or from or the
you can also use C2, I think C2 and C4 lines. But apart from that, Herschel far IR emission are like really sensitive for young stellar objects. But my another question is related to your Perseus analysis. So I know your basic machine training algorithm is mainly focused on CO line, and which is I think 1 to 2, 0 to 1 emission.
1 to 0. Yeah, 1 to 0.
Yeah, I'm sorry. And did you also try to correlate your detections maybe in other emission line, for example, recombination lines in hydrogen and all,
Yeah,
and then see if you miss anything?
Yeah, sure. That's straightforward. We want to do that to extend our method to different traces.
So what's the result? Have you done that?
No, we are planning to do that. Since we have ammonia data, so the first one is extend to ammonia, the more dense gas tracer. And then we have HCl plus data. So we want to extend to that. And also there is higher J transition data, 3 to 2, observed by JCMT. They have a large sky survey across Milky Way. And that's also a good data set for us to apply to. We will do that.
Yeah, and also I think Planck observed in both 1 to 0 and from 2 to 1 as well. So it is like 3, if I'm not wrong, 3 arc minutes resolution. It's 2048 N side. So maybe I'm not sure whether that is sufficient for your analysis.
And also for the resolution here, we are using a really coarse resolution because we assume a 13-meter telescope observing Taurus and Orion. If there are some larger telescope, we could extend our data to further distance. And also in our training sets, we include different resolution. We assume the clouds at several different distances. And then we have already implemented different resolution in our training set.
I see. Thanks for the information.
We have time for one more question, if there's any. If not, let's thank you. And you're up for a discussion with grad students. Okay, thanks everyone.